The first thing is that there are magnetic fields. So we are going to study magnetic fields and charges that are moving through magnetic fields. So B is like electric field. There's a different field which we call magnetic field. Now we need to study this in 2-3 ways. One is to study the effect of magnetic field. What does it do? Effect on charges. Then we have effects of magnetic field on wires or current. Then what produces magnetic field? Currents produce magnetic field, right? So therefore, this is the second part where we have to study I, how does it produce B? For a long time people did not realize that currents produce magnetic fields. So what did they think produces magnetic fields? In fact, even before electric fields were studied, magnetic fields were studied. So what did people think? Basically magnets produce magnetic fields, right? People already had a very clear picture. I mean, all of you have played around with magnets a little bit, right? So you know that magnets push at a distance. Electric charges are not that easy to kind of capture and then play around with. But magnets are very simple. So people have been playing around with magnets for ages. So they know that magnets do something to each other. And the first idea is that magnets create a magnetic field. Now the fact that actually magnets, whatever they are actually very small atomic level currents is an idea that came up much later. So but the way we are going to study is to first assume that there is a magnetic field. What does it do to charges? What does it do to current? Once you understand this and once you can calculate this, then we will look at how are these magnetic fields produced by currents. Much later we will worry about magnets and what kind of magnetic fields do magnets produce. Magnets can just be modeled as a wire like that, a solenoid, and once we get that point, then we know the answers for solenoid because we would have by that time hopefully studied how currents produce magnetic fields. Once we know this, then we can basically understand magnets. Historically it was exactly the reverse. People started with magnets, then they had the idea of magnetic fields, then came up the idea of electric fields, even much later. So magnets always people realized was doing something at a distance. Okay, that is where the starting point was. Anyway, so right now we are going to first focus on what magnetic fields do to charges. The formulas here are a little bit more messy than for electric fields. Suppose I say there is an electric field here, E, and I had a charge Q there or here or wherever. Let's say this whole thing was electric fields in this direction, filling out this entire place, and let's say this was charge Q. It has a force QE in the direction of the field. Okay, so it's a very simple idea. But if the same charge was in a magnetic field, so let us say that the magnetic field is this way, B, and you just place this charge here. It turns out it has no force, doesn't feel any force. Okay, but if this charge is moving, then it feels a force. In fact, if the charge is moving like this with some velocity, how much force do you think it feels? It still does not feel any force. But if its velocity was pointed at some other direction, let us say this direction, then it feels a force. So the force clearly depends on the velocity, because if the velocity is in this direction, it feels no force. If it was at rest, it feels no force. But if the velocity is some other angle, it does feel a force, and the force that it feels happens to be in this direction. Actually, if it was a positive charge, it feels it in that direction. What I mean is that it is perpendicular to the board. Okay, the way I have drawn it, it feels the force in that direction. If it had a velocity in this way, then it will feel a force in this direction. Now, clearly that means that the force is perpendicular to V as well as B, and we already know a nice vector operation which basically produces a perpendicular, which is cross product. Why does this B produce a force in that direction? Well, that's a much harder question, okay, to which I have no answer. It is like asking, why does one mass attract another mass? We know that it does. I can tell you the formula for it. I can tell you that this is what happens when two things are pulling each other. Why does a magnetic field exert weird kind of forces in this direction or this direction? Makes it sound like this is somehow obvious and that is not so obvious. All I can tell you is this is also not so obvious. Why should there be electric fields and why should they push charges? Is that better? Is that very clear? It looks like, okay, it must be pushing it in the direction of E. No, your calculation is easy, that's all. Or it looks at least easy. There is no meaning to this either, no, in some sense. If there is a field like this, why should the force be that way? You are asking me the question, why should the force be this way or that way? Because it looks a little bit weird. But that is also equally weird. Right? You would have thought first that force should be in the direction of the field. I am just telling you it is not. Do you think the first set of people who realized that the force was in some direction assumed the field was in some other direction? What do you think? What do you think they would have assumed? It would have been in the same direction. If somebody is pushing that way, they assume that something must be there. Long time ago, when people had this idea of, when they realized that the earth was going around the sun, that itself took a long time, but if the earth is going this way, which way do you think it requires to be pushed? Today, of course, you know that it actually gets pulled that way. But at that time, if something is going that way, which way do you think they would have assumed it should be pushed? This way. So people assume that there must be somebody standing there and flapping their wings and pushing the earth. And it makes a lot of sense because the first assumption is you are going this way, somebody should better push you this way. Now if this guy feels a force like this, you assume that the magnet must do this. Okay. Now we are building on top of a lot of other experiments. So therefore, we know that if you assume that the magnetic field is this way and you change the velocity, then the force changes direction. Okay, if the magnetic field was this way because the force was this way, now suppose I make the velocity point like this. Which way will you end up getting the force? That way. Now you have to assume that because the object is moving like this, the magnetic field is that way. That means the magnetic field is changing based on this object. But it's somebody else's magnetic field. Somebody else is producing the magnetic field. How do they know what velocity this guy will go with? Lands us in a lot of trouble. The basic point is, experiments tell us that the magnetic field, if you assume in some direction and you try to look for the best way to figure this out, you have to accept the idea that the force is pointing that way. Okay. Fundamental rule. No logic behind it. But you can ask, why is there even a magnetic field? And there are good reasons if you go backwards. If there are electric fields, it turns out that with relativity you do need magnetic fields. That was not how it was discovered, and that is not the best way to understand it either. Okay. It is like saying, to understand gravity, I do need gravity because if I ignore this and have Newton's first law, this guy will go there on its own. But this guy does not go there because straight line motion is what Newton's first law says. Objects want to go in a straight line. Simplest solution is to say objects want to go in ellipses around the sun. Finished. Okay, then I don't need any more explanation. But then, why does this fellow fall down? Well, this object wants to fall down. Okay, for everything if I say that's what it wants to do, then there is no more explanation required. We should do slightly better than that. So what we do, or what Newton did, was to say objects want to go in a straight line with constant velocity. Now if they are not doing that, for that I will give you a reason. Why do they want to do this? That's what they want to do. I don't know. Okay, so we start with something that we assume as a fundamental law and everything else we try to explain. So this we say, well, if this guy wasn't there but was here, this probably was caused by the sun, and then we bring in some formulas to explain how the force acts. Why does the force act like that? That's how it acts. Okay, so we are right now not trying to figure out how to create this. We are not creating this, right? This is what is there. So we only try to analyze it. The same way, this thing, there is a force that acts on this guy. How do we know? Experimentally we know this. Now, I don't think when they started with cross products. In fact, they didn't even have the notion of a vector. They just found out that at various different directions, the force also goes in different directions. Today, you summarize all of those experiments, you say, well, if the V is this way and B is this way, the force is perpendicular to both V and B, and we have a nice way of writing it. This vector is perpendicular to V and B. It also depends on the size of the charge, and it turns out that this is the force. Okay? Now, there is no derived explanation that you can bring to this. But starting from this, you can derive everything else. So, we are going to take this as a fundamental statement about either magnetic field or as force produced by magnetic field.